I'm audible, ma'am?
Yes, you are
Okay.
audible and slide is there.
Okay, ma'am. Okay, so first of all, I am thankful to the organizing committee to give me opportunity to present my work. So my presentation is the transcription of heterogeneous catalyst for the efficient biodiesel productions. Sliding is changing, ma'am. Sliding is changing.
Yeah, okay,
Okay.
good.
Okay, thank you, ma'am. So biodiesel is chemically we know that is called as the fatty acid methyl ester. So we can use this biodiesel in place of the different type of the diesel engine. So they are the different type of the advantages as compared to this biodiesel as compared to the diesel, because this is the renewable source of the energy. We can produce this biodiesel by using different type of the vegetable oil. This may be the edible or non-edible oils. We can use the animal fat, waste chicken fat, waste mutton fat. So for the production of the biodiesel is we can use the one chemical process that is called as the transesterification process. So in this process, we can use the catalyst. It may be the enzyme-based catalyst, it may be the acid-based catalyst, it may be the alkali-based catalyst. So for this one, so we can react with the different type of the vegetable oils, animal fat oil, with react with the methanol. Mainly we can use different type of the other alcohol, but we prefer the alcohol that is the methanol, and we will get the biodiesel and the byproduct that is the glycerol. So there's a lot of the advantage of the glycerol, different type of the pharmaceutical industry and other type of the industry we can use, and we can use this biodiesel in the process for the production of the biodiesel that is the fatty acid methyl ester. So if we see the chemical process, the transcription process, so first one that is the triglyceride that is called as the parent oil, and it we can be obtained this triglyceride from different type of the oils. It may be animal fat, waste animal egg, or we can use the methanol. So in this ones, the if we use the 3 mole of the methanol, so the process is the reversible. But we can use the 6 mole of the ethanol. So in that ones, we can use the higher concentration of methanol. So the reaction will be go to the forward direction, and we will get the methyl ester that is the biodiesel, and the byproduct is called as the glycerol. So for the basis of this transcription process, we can use the catalyst, like we are using the alkali, so that is called as the alkali. If we use the acid catalyst, and we use the enzymes, mainly we use the lipase enzyme, so that is called as the enzyme catalyzed transcription process. But it was reported that if we use the alkali-based catalyst, the reaction is much more faster as compared to the acid and the enzyme catalyst. For this, so we prefer the alkali-based transcription process. So in this process, there are the two type of the catalyst, homogeneous and the heterogeneous catalyst. The homogeneous catalyst like the sodium hydroxide, potassium hydroxide, so we can use this one, so it is dissolved in the methanol, so we cannot further use that type of the catalyst. But if we use the heterogeneous catalyst like the titanium oxide, calcium oxide, zinc oxide, magnesium oxide, so in that ones we can reuse the catalyst, and it has been easy to separation process, recyclability, and have the lower environmental impact. So we prefer the heterogeneous catalyst. So heterogeneous catalyst, which is mainly from the alkaline earth metal and different type of the alkali metal. So in this process, we use the calcium oxide, magnesium oxide, zinc oxide, titanium oxide, and the aluminosilicate. So in this process, we use the calcium oxide and the titanium oxide. So this is the particle, nanoparticle. What are different type of the nanoparticle? So there is the application of the nanoparticle. So in that ones, it can be used the chemistry, environmental testing, automobile, electronic, pharmaceutical, and the biotechnology. But in case of the renewable energy, in mainly the renewable energy, so we can use this different type of the nano catalyst in the biodiesel production, biogas production, biohydrogen production, and the bioethanol productions. So in this ones, we have synthesized the two type of the heterogeneous catalyst like the calcium oxide and the titanium oxide. This is the application of the titanium oxide. It can be used the wastewater treatment, CD culture, road construction, biofuels, solar battery. So in this ones, we have chosen the application of the titanium oxide as in the biodiesel production. So for that one's material and method, first of all, we collected the waste chicken fat, different type of the slaughterhouse, and we check the what is the property, physiochemical property of that one. So in that one, the much more important that is the acid value and the free fatty acid content. So this acid value, that is the 4.36. So for that one, it shows that we go to the process of the esterification and the transesterification process. If we go directly to the transesterification process, so there's a chances of the soap formation. So for that ones, we synthesize the calcium oxide nanoparticle. So for that ones, we have used the eggshell, and in that ones we crushed in that ones dried in a hot air oven, and with the grinding was done with the help of the moisture petal. After that ones we have calcinated, so in that very high temperature 850 degrees centigrade for 4 hours, and to obtain the calcium oxide nanoparticle. And we synthesize the another type of the nanoparticle, that is the titanium oxide nanoparticle. In that ones we have the titanium tetrachloride added in the ethanol, we cool down, added the ammonium hydroxide, precipitated, washed with the distilled water 2 to 3 times. After that ones we will get the titanium oxide, so we have the calcinated at the very high temperature 850 degree for the 3 hours. So for this ones, because in that ones we have used the raw material, that is the waste chicken fat. So in that ones the acid value, that is the very high. So for that ones we go to the process of esterification. After that ones we go for the transesterification process. So for the acid transesterification process, we use the toluene sulfonic acid, and we have used the catalyst 0.5 and the molar ratio. After that ones we go to the alkali phase transesterification process. So in that ones we have used the calcium oxide and the titanium oxide we added, and in that ones we have not used the temperature, but in that ones we have used the microwave. So in that ones the process is completed within the 2 to 3 minutes, and if you use the conventional process, we go for the heating. In that ones it take around the around the 1 to 2 hours, but in that ones we have the microwave assisted transesterification process, so the process is completed within the 2 to 3 minutes. After that ones we will get the biodiesel and the glycerol. General discussion. So for that ones we have characterized the calcium oxide nanoparticle. So in that ones this is the FTIR, and it shows the absorption spectrum, that is the 6x centimeter inverse, and this is the formation of the hydrate. And we have performed the XRD analysis. So in that ones we have calculated what is the 2 theta value of different peak size, and that is the particle size, what is the 43.2 nanometers. And with the help of the JCPS database, we have reported that the car number, that is the 1497, and this is the calcium oxide nanoparticle, that is the phase center cubic. After that ones we have go for the characterization of with the help of the same, and in that ones they have the large porous material as corresponding to the basic site of the catalyst. After that ones we perform the TEM analysis of the particle, and it shows that is the smaller size, it shows as the high surface area, and we calculate what is the average nanoparticle size, that is around the 43 nanometer, and it is similar with the XRD analysis. After that ones, what we do, we have synthesized the nanoparticle, we characterize the nanoparticle. After that ones, we have used this type of the nanocatalyst for the transesterification process for the biodiesel. So in that ones, when we increase the concentration of the nanocatalyst from 1% to the 5%, so there is an increase in the biodiesel yield, that is the FM yield. But if we go beyond the 5% of the optimum concentration, it is decrease in the FAME, that is the biodiesel yield is decreased due to the mass transfer limitations. After that ones, we have optimized what is the oil ratio with respect to the methanol. So in that ones, methanol to oil ratio changes from 3 to 1, and in that cases we have used the optimum concentration of the catalyst, that is the 5%, and in that cases we get the yield of the 72.3%. We have also optimized what is the temperature, what should be the agitation for during the transesterification process. After that, once the biodiesel is synthesized, we go for the characterization of the FAME. So density was the 0.86, and that is 0.83 of the petroleum diesel. And we have compared this with the ASTM database. So in that one, the viscosity is same. The heating value, that is around the 41, and the reported petroleum, that is around the 40 to 45 megajoule per kilogram. So in that ones, we can use this biodiesel in the diesel engine. So for that ones, we can use the blend forms, like we can use the B20, means 20% of the biodiesel and 80% of the petroleum diesel. So in that ones, there is no need of the modification of the engine, existing engine. But if we go beyond the concentration of that is the 50 to 30 or 50, that ones we can modify that as the diesel engine. All right, when we come to the conclusion, so concentration of the catalyst, that is around the 5%, and methanol to oil ratio, it is 9 to 1%, and we will get the maximum biodiesel, that is 80%. And so in this process, so we can use the microvessel transfer process, so it can reduce the reaction times, it can be increase the yield, and with the help of the heterogeneous catalyst, it is the easy to separation process, and this transcription process is the good, unique thermal effect and beneficial to the
Dr. Kumar
chemical.
Gaurav,
Yes, ma'am.
you're requested to please switch on your camera because it's already mentioned in the mail that you have to switch on your camera every time.
Okay, ma'am. Okay, ma'am.
Okay.
Okay,
And
ma'am.
it is for all the participants.
Okay, ma'am. Okay, so that was all my presentation. Thank you. Thank you all for the listening this
Thank
one.
you so much for your conference, sir. Myself, Dr. Arun Raja, Assistant Professor, Department of Communication, K.S. Rangasam Raja, Washington Science, Kitchen Road. My research area is tuning gas sensing properties in chemically synthesized zinc oxide doped cadmium sulfide nanocomposite through annealing graphite. Now, going to start with introduction. The cadmium sulfide is one of the predominant material in semiconductor. And approximately the band gap is 2.42 electron volt, approximately 515 nanometer. The seed is the highly interesting material for nanocomposite photovoltaic. And the cadmium sulfide has crystal cubic structure or hexagonal structure also. And the cadmium sulfide and the sodium sulfide both are precursor material for my research area because most of the researchers did cadmium sulfide, cadmium nitrate, cadmium chloride, and the thiourea also. So here I have only few researchers only did cadmium sulfide and the sodium sulfide as the precursor material. That's why I have used this. And the series Zetanol is an important material for the solid state devices such as solar cell, thin film transistor, gas sensor, and the light emitter diodes. And we have a number of gas sensors available here. All the sensors are usually in this my area. Now the catalysis techniques. We have 7 catalysis techniques are available: XRD and the particle size analyzer and the Fourier transform interference spectroscopy (FTIR) and the SEM scanning electron microscopy and the UV visible spectrometer and the photoluminescence spectro and the TEM transmission electron microscopy. Now start with synthesis work. The cadmium sulfide. The cadmium sulfide 0.1 mole is mixed with deionized water with 30 ml of water and the stirrer for 10 minutes only. Then sodium sulfide is mixed with deionized water with 30 ml of water and the stirrer 10 minutes. After that, the cadmium sulfide and the sodium sulfide is stirred 40 minutes. And finally, zinc acetate. The zinc acetate is mixed with deionized water with 30 ml of deionized water. Finally, we got cadmium sulfide and zinc acetate is mixed with dried at 373 for 48 hours in hot air oven. Finally, the samples was annealed at 473 Kelvin for 1 hour at air atmosphere. Finally, we got it Zetanol CDS nanocomposite. Then we have 2 chemical methods are implemented. That is, one is chemical precipitation method and another one is salt gel method. Now start with XRD. The XRD is Zetanol is a hexagonal structure, and the CDS also is a hexagonal structure. The JCP is like this. The particles annealed at 473 Kelvin exhibit the main peak 002 crystal plant as the preferred orientation and the intensity in strong annealing temperature. Further, it was found the average particle size is 43.9 to 44.2 nanometer. It is approximately nanometer in XRD. The next is UV visible spectroscopy. It reveals that during annealing, the absorption edge undergoes a slight tilt toward the higher wavelength. The absorption range is 380 nanometer and 400 nanometer in the Zetanol series and annealing with 473 Kelvin like this. And the direct band gap between 3.2 and 3.1 electron volt. That is, the direct band gap is by Max Planck energy equation like this. It is important to note that an increase in particle size can lead to lower band gap level as a result of the effect of quantum size. Here, this 380 nanometer for Zetanol series, and after annealing that, the nanometer size is increased 400 nanometer due to annealing temperature. the same images. The same images is recorded at 1 and 0.5 micrometer. So the shapeless and the polycrystalline nanostructure, zetano-CDS nanocomposite. And the image of the annulate zetano-CDS sulfide possible have looked at a small irregular agglomerated crystalline morphology. Further, the same images confirm that the sample annulate at 423 Kelvin had been operated like irregular stacked aggregated nanostructure. On the photoluminescence, we have 4 green emission band like this: 361, 394, 458, 490, 520, 540 were observed in the photoluminescence spectroscopy. And the PL spectra of zetano-CDS on at 473 Kelvin exhibit a broad field around at 490 nanometer. The green emission band series nanoparticle is 495 nanometer, but the oxygen vacuum of zetano is 458 nanometer, is approximately nearby our area. It is clear to indicate that absorption of peak is slightly shifted to longer wavelength during the annealing process. The recombination of the defect the excitation status induced by zetano provides modified surface area in the luminous band. Like this, 361, 394, 458 gradually increase due to annealing temperature. So the particle size distribution, the average size of the particle zetano-CDS and annealing at 4,000 Kelvin observed was 42 and 47 nanometer respectively. Both samples exhibit high similar particle size with minimal disparity observed between the as preferred samples. And TIM images. TIM images like that annealing sample exhibit the speckle shaped nanoparticles. Like this, picture A is 50 nanometer and the picture B is 20 nanometer due to annealing temperature. That is FTS spectra, the 608 CDS stretching because my important material is core material is cadmium sulfide. The carbon sulfide stitching is 608 and the sodium sulfide is 1105 and the sulfide group is covered 1336 and 1590 and the CH stretching of EDTA 2935 and that is a additional composite of zetano-CDS nanoprotein and 3470 OH stretching due to presence of moisture in the sample. That is a FTR spectra of zetano-CDS and the zetano-CDS 473K nanocomposite. That is my application gas sensing measurement system like that LCR meter, inductance capacitor resistance meter, and the gas chamber. My material, my pellet is input in the gas chamber. So we have two gas sensors available. By my sensor range is only oxygen level. That is a gas sensing measurement system. There is a gas sensing mechanism. My mechanism is start with LCR meter, approximately frequency is 100 hertz, and the constant pressure in 1.75 kilograms centimeter per square. There is a sensor response. Oxygen sensor response in my CDS nanocomposite material. That is a time-dependent change in the resistance of zetano-CDS. Before measuring the oxygen response, dry air was continuously passed through the glass chamber to remove the organic impurities. Then, oxygen gas was allowed to pass through the gas chamber through inlet valve. The change in the resistance of CDS sensing as a function of the time at the moment of gas turn off and turn off is monitored. To assess the zinc oxide cadmium sulfide nanocomposite gas sensing capabilities, the gas concentration is from 50 to 250 ppm. ppm is parts per million. That is A is zetano-CDS gas sensor application and B is annealing with 473 Kelvin. Here the response gas sensing performance. Here we note that picture A zetano-CDS the gradually increased. Initially the range is 1.6 sensor response is gradually increased up to 2.3 megohm. After the annealing temperature, the range is between 1.8 megohm to 2.6 megohm. So before annealing temperature is low, and after annealing temperature is the oxygen response is high. Is compared with CDS nanoparticle. The total response time of the sensor of the zinc oxide carbon sulfate was considerably better than that of the nanocomposite it was manufactured. The stability of Jetango. The determined the material's resistance level of gases gas range from 50 to
Please
250
compile your
meters.
work.
Oh, yeah,
Otherwise,
fine.
I will compile work.
That is the conclusion. The accepted pattern confirm example phase of CDS and annealing introduces structure changes correlating with other property alternation. FTR only speaks reverse chemical information, altering inside properties and composition. It's the particle size and the both zinc oxide, carbon sulfate, 473 Kelvin nanotemperature responded to varying oxygen gas concentration with the annealed sample exhibiting it can sensitivity and stability due to the structure and the surface modification. Finally, this nanocomposite, Jetango CDS 470 Kelvin nanocomposite will be more effective for the development of gas sensor and the optoelectronic materials. It's a reference of my purpose and research area. Thank you.
Okay. Good afternoon, everyone. The title of my talk is Exact Solution of Optical Pulses in Nonlinear Metamaterials. The outline of my talk is as follows. First, I'll talk about the introduction, then brief discussion on metamaterials, then method and model, the results and discussion, and finally the conclusion. First of all, why is this problem interesting? The reason is, since the nonlinear wave propagation in optics has led to numerous innovations in various fields, like the most notable of which are like fiber optics and surface dynamics, there are also several investigations to study the nonlinear propagation of ultra-short pulses in dispersive media. Now, many results have already been found in linear medium where the dielectric permittivity and the magnetic permeability are actually not dependent on the electromagnetic field intensities. So in this case, the nonlinear metamaterials are obtained by embedding an array of thin wires and split ring resonator structures in a nonlinear dielectric medium. In this work, a unique method has been used to exactly solve the nonlinear Schrodinger's equation in a dispersive medium. So basically, dispersive means here the dielectric permittivity and the magnetic permeability both are dispersive and basically they're negative in nature. So that's what we deal for the negative refractive index medium. And the main thing is that these negative refractive materials are not naturally available. These are just structured materials which are artificially structured at microscopic length scales at a variety of wavelengths. And finding a natural material having a negative refractive index is not possible. So that's why they're synthesized by putting together two structured materials which separately show negative dielectric permittivity and negative magnetic permeability. And the resulting structure, composite structure, possesses a negative refractive index. So here, this is what we understand by NRM. So here, as we already know that the refractive index of a material is a measure of the optical density where we take the ratio of C and V. Where C is the speed of light in vacuum and V is the speed of the electromagnetic wave inside of the medium. According to the Maxwell's equations, the refractive index is taken as a square root of epsilon and mu. So basically, in all media which are physically available to us, so we basically take the positive sign here. However, the refractive index is taken as a complex square root here, having both real and the imaginary parts. And epsilon and mu are in general these complex functions of the frequency, and they are dispersive in nature. So in 1967, Veselago first considered the case of a medium having a negative refractive index, where he considered the negative square root of epsilon mu. And that's what actually has been studied by Smith in an experimental group. So here in this case, so all the materials are actually divided into 4 quadrants where the epsilon is taken in the x-axis and the mu is taken in the y-axis. In the first quadrant, we see that both of them are positive. And these are the ordinary optical materials, or these are also called as right-handed propagating waves, because in this case, the propagation vector K, E, and H, so all three, they form a right-handed triad. So when we look to the second quadrant, we see that epsilon is negative, however, mu is positive. This is the case for electrical plasma. So here, basically, since the refractive index becomes imaginary, which leads to the propagation constant also becoming imaginary. So that's why the waves actually become decaying there. And we get evanescent decaying waves, which means that these are the near field waves which exhibit exponential decay with distance, and which are formed when the sinusoidal waves get internally reflected off an interface at an angle greater than the critical angle. So that total internal reflection occurs. I think this term is very much familiar to all of us. Then when we see the fourth quadrant, also we see similar features when epsilon is positive but mu is negative, and that leads to a magnetic plasma. And in the region in quadrant 3, we see that both epsilon and mu are negative. So in this case, we got the negative refractive index medium, where we see that K, E, and H form a left-handed triad, and that's why they're called the left-handed propagating waves. And to achieve this NRM, so we basically take this negative dielectric medium, and both minus epsilon minus mu both has to be obtained. To get a negative dielectric permittivity, basically the wire mesh structure is obtained. So here the dielectric constant for a system is represented by a Lorentz-Dode model, so which is the most convenient model known to us. And in case of a metal, so we know that the electrons are not actually bound to the nucleus, and therefore the resonant frequency omega naught actually tends to 0. So in this case, F is a filling factor and omega p is a plasma frequency. So when omega naught tends to 0, we see that there is a negative sign which comes in between. It means that when the frequency is less than the plasma frequency, epsilon automatically becomes negative. So to obtain this kind of medium, so basically we take a thin wire structure. So here these are actually taken in the sub-wavelength limit. That is, the incident radiation, basically the wavelength of the incident radiation is much higher as compared to the dimension of the spacing and the radius of the thin wire structures. So also this kind of three-dimensional structures or orientation of the wires can also be taken to obtain a better performance in terms of this dielectric permittivity. Then here, to obtain the negative magnetic permeability, split ring resonator structures are obtained. So here we can see that the magnetic field is applied along the axis of the metallic cylinders. And if we take a cross section of that, actually we take this kind of gap ring structures. And we actually take Swiss roll structures also to get the negative magnetic permeability result. So here basically there are some circumferential currents which arise actually because of applied the magnetic field, and that actually gives rise to the inductance, and the gap between the rings actually gives rise to the capacitance, and they together actually give rise to some magnetic resonant frequency. And the 3D picture is also seen here. So here the SRR structures are aligned along the 3 directions. So here similarly we can have the applied magnetic field and the average magnetic field outside the cylinder, and if we take the ratio, we get the effective magnetic permeability. So here we see that this is actually for this particular structure of the SRR structure. So we are having this kind of mu effective. And the resonant frequency, this here arises, as I have already said, that this arises due to the LC resonance of the system. And for frequencies larger than this omega naught is the resonant frequency, mu is negative up to the magnetic plasma frequency. And here, if we just embed this bulk of this thin wires and the split ring resonant structures inside the nonlinear dielectric mediums, we get actually a composite NRM structure. So that's how it looks like this. And here is the theoretical model. So optical pulses in nonlinear metamaterials. So here the generalized nonlinear scrodic written in this expression. So basically it's a nonlinear medium, and where the
Dr. Lipsa, please conclude first.
and the Lorentz-Dode model. This equation one can also be field and the respectively. City dispersion module, and minus A4 is a self-depending term, and A5 is a friend.
So it seems there is some internet connection problem.
Equations, and here to different medium. So we see that when the frequency is greater than plasma frequency, we see that the x-axis is so one denotes actually the electrical plasma frequency. When the frequency is more than the electrical plasma frequency, so it is a positive. scaled frequency. So when the frequency is less, both epsilon and mu are negative. So that is the negative rotating reason, which is shown. We can see that these coefficients in the nonlinear Schrodinger's equations are defined this way. So these are also plotted. So here individually you can see that which term is contributing in which way. So that can be clearly analyzed by looking at this curve. Then here are the results. So the generic form of the electric field is basically given by this E equal to rho e to the power of I chi, where the E is just a envelope. I mean, it's the envelope of the electric field, and here rho and chi are actually some real functions of xi or zeta, which is a traveling coordinate and given as eta into z minus vzt, where eta is the width parameter. So by just substituting this in the earlier expression of this Schrodinger's equation, so we see that since the right hand side is 0, so individually, because this is a complex form of the field, so we can have the real and the imaginary part separately giving 0 to us, and they can be represented by a set of coupled equations, which are represented by equation number 3 and 4. And after integrating this equation number 4, so we get this derivative of the phase chi. So here that is actually essential to just plug in the value in equation number 3, and k1 is the integration constant. So by doing this analytical calculations, so after substituting this in the earlier expression, so we have this kind of expression which is a little bit complicated. And finally, we have also another integration constant k2. And by doing some analytical calculation, so finally, so we do some substitution like f some other parameters, which is also a real function. So that is taken as rho is equal to square root of f plus h some other constant is introduced, which is taken to be 0 for some convenience. Then some square factor will be there, which has the coefficient of that has to be taken to 0, because we need a cubic equation to solve for the nonlinear Schrodinger's equation, and that is expressed by equation number 8. And the non-trivial solution of equation number 8 are mostly of rational type, which are given by this expression a plus b f1 square by 1 plus d f1 square. So this is the convenient way to represent the solution of a nonlinear Schrodinger's equation. And there are various solutions which can be considered. So for example, the sinusoidal solutions. So here, these are represented as C and xi, where xi is already known to us, that is the traveling coordinate, and m is the modulus parameter. So by taking the different values of the modulus parameter, actually the different solutions can be obtained. So here the first solution which we take is a trigonometric solution where we put m as 0. And by doing some manipulations, some analytical calculations, so here we have some C3 by C1 ratio and cos square xi by 1 minus 2, 3 cos square xi. So basically for m equal to 0, we have this kind of periodic solution where we have a cosine function. So this actually gives us the final representation of the intensity inside the nonlinear metamaterial when the pulse is propagating inside the nonlinear metamaterial basically. And here are the results. So here we plot the intensity inside the NRM region, which we take as a function of the scaled frequency and the traveling coordinate. So we see that the periodic solutions are well established here, and we can clearly see that when we go to the higher frequency side towards the magnetic plasma frequency, we see that the peak of the intensity curves basically decreases. And that basically happens due to the dispersion inside the NRM region. So that is a very important result. And another thing is that to understand this intensity curve in a better way, so we choose a particular frequency, say in between this range in the NRM region. So here I just insist that this NRM region is always obtained in a particular frequency range only. So it cannot be obtained anywhere. I mean, a particular frequency only has to be selected. So here within this range only a particular frequency has been selected, and then the intensity has been plotted with respect to this z is a spatial coordinate and time. So here we see that the solitonic form of the solution is well established. So this gives us stability of the solution. So the stability of the solution mainly arises because of two factors. Like here, there are two bases of attraction basically are present here. One is that the part of the solutions are mainly arising or lying inside the region where we are having a periodic attractor, and a part of the solution is lying in the region where we are having zero intensity. So that actually gives rise to the stability of the solution, and that is very, very important when the pulses actually propagate inside a nonlinear medium. So these are the results we have obtained. And finally, the conclusion. The exact solution of an optical pulse propagating in a nonlinear dispersive medium has been obtained using an analytical and simulation-based method. Then intensity curve has been analyzed in a metamaterial or a negative refractive index medium, where the peak decreases with increase in frequency. The stability of the solution is observed from the intensity curve, and the future direction will be to study the surface wave states at the interface of a positive refractive index medium and a negative refractive index medium. And here are the references which can be referred for this work. And I thank my PhD supervisor, Professor S.A. Ramakrishna, for giving his valuable suggestions. Also, my sincere thanks to my collaborators, Professor P. Panikrai and Dr. Sachin Saw, for helpful discussions. I also thank Panchayat College Bargarh and KIT University Bhubaneswar for support.
My topic is biosynthesis of silver nanoparticles using Pisidium catalinum leaf extract and their antimicrobial activity. This is nothing but a strawberry guava. You can say it's a strawberry guava. Actually, it is native fruit of Brazil, and this fruit is a juicy fruit with excellent flavor, and it is used for a herbal medicine among the local people of Brazil. It is also used to make juice, jams, and also many applications in food industry too. So it is an unrecognized tropical tree in Indian subcontinent, and the fruits are rich in secondary metabolites. So the leaves of this tree have been investigated by very few for their biological activity. So what is the aim and the objective of my study is, the aim of the present study was to analyze the phytoconstituents, bioactive compounds, which is present in strawberry guava leaves, and to synthesize silver nanoparticles and evaluate antimicrobial property. The objective of my study is to perform both qualitative and quantitative phytochemical screening and to identify the bioactive compounds using GCMS analysis, and to synthesize silver nanoparticles and characterize by using UV visible FTR HR10. And finally, to evaluate the antimicrobial property by using both crude extract and synthesized silver nanoparticles. So coming to the materials and method, a collection of plant material. So the plant material was collected in Kodaikanal, Tamil Nadu, and preparation of extract by using a different solvents, ethanol, methanol, aqueous, and hexane. So both polar and non-polar solvents. And go for qualitative phytochemical screening, and quantitative phytochemical screening was done. And then go for the synthesis of silver nanoparticles and characterization, and finally go for antimicrobial activity by well diffusion method by using a two organism, Candida albicans and Candida tropicalis. So coming to the result. So qualitative phytochemical screening of Pisidium catalinum leaves, that is strawberry guava. So here the qualitative phytochemical analysis of leaf extracts of various solvent showed the presence of plant metabolites, namely alkaloids, phenols, flavonoids, saponins, terpenoids, glycosides, and sterols. The next one is a quantitative phytochemical screening of strawberry guava. So here for quantitative determination, I have chosen a phenol and flavonoid because rich content of antioxidant property. So for here, the aqueous extract of strawberry guava leaves showed high phenol content. The value is 6.5 mg per gram, whereas lowest in ethanol extracts, that is 14.2 mg per gram. So quantitative determinations of flavonoid in the leaf extracts of strawberry guava, especially in aqueous extract, it showed highest flavonoid content the value is 57.0 mg per gram, and the lowest value was observed in ethanol, 32.4 mg per gram. So further, go for the bioactive compounds which is present in the strawberry guava leaves by using GCMS analysis to find out the bioactive compounds from different solvents. So here, GCMS analysis of ethanol extracts. So we got nearly 10 compounds. So the humulin, so methyl salicylate, so many compounds. It plays a major role in anti-inflammatory, antimicrobial, and anti-tumor properties. Similarly, we go for the GCMS analysis of methanol extract, hexane extract, as well as aqueous extracts. All are shows a good bioactive compounds with biological properties. So coming to the synthesis of nanoparticles using Pisidium catalinum, that is strawberry guava leaf extracts. So here the silver nanoparticles synthesized from the leaves, it showed a short peak at 460 nanometer and a broad peak at 436 nanometer. It confirms that the presence of silver nanoparticles from aqueous extracts of leaves. So the next one is the FDR spectrum of silver nanoparticles. So in order to identify the surface structure of silver nanoparticles and identify the possible functional groups of the plant extract, which is involved in the synthesis and the stabilization of silver nanoparticles, by comparing the FDR spectrum of the plant extract and the synthesized silver nanoparticles, the band shift and intensity decrease of hydroxyl, carbonyl, and amine groups were observed. It indicates that the major phytochemicals from the extracts involved in reduction and stabilization process and coated on silver nanoparticle surfaces. The next one is an XRD pattern. So here, the Pisidium catalinum silver nanoparticles indicate that the structure of silver nanoparticle is face-centered cubic. So coming to the HR-TEM analysis. So here, the TEM image of the silver nanoparticle sample shows the nanoparticles exhibit a typical spherical morphology, and the particle diameter was found to be the range 8 to 18 nanometer. So coming to the SAD pattern. So here the ring-like diffraction pattern in SAD image indicates that the Pisidium catalinum silver nanoparticles are purely crystalline in nature and could be on the basis of self-centered cubic silver, which is consistent with XRD analysis. So coming to the antimicrobial property of both crude extract and silver nanoparticles. So here in this picture, so we have selected two organisms, that is a fungal organisms, that is Candida albicans and Candida tropicalis. It is a human pathogen. So here, when treated with the aqueous extract of strawberry guava leaves, so here a zone of inhibition was found, 12 millimeter at 20 μg per ml concentration against Candida albicans, whereas in Candida tropicalis, it showed 11 millimeter zone of inhibition was observed at the concentration of 20 μg per ml. So in silver nanoparticles, here exhibit a zone of inhibition. It's a 26 millimeter at 20 μg per ml concentration against Candida albicans. Whereas in the Candida tropicalis, the zone of inhibition showed 13, it's a millimeter. So I want to conclude from this study. The present study showed that the strawberry guava leaves showed abundant in phenol and flavonoid content and contained innumerable bioactive compounds with antibacterial, antifungal, antiviral, anti-cancer, anti-inflammatory, anti-diabetic, and anti-aging properties. So the Pisidium catalinum leaves must be investigated further to identify the lead molecule in them that might help in drug designing to target a numerous diseases. Thank you.
First of all, I would like to thank the organizing committee members to give me chance to present my research work here. And good evening, all of you present here. So my today's topic is on the DFT calculation of molecular interaction of curcumin with silver nanocluster. So actually, silver, as we all know that the curcumin, which is also called haldi, so it is of very much importance in our daily life. We use it everywhere in our kitchen also, and in the lab also. So it is of very much importance. Just a minute. Let me show slides. Okay. So curcumin is of very much importance. In this lecture today, in today's lecture, I will be explaining on the molecular synthesis of this silver nanoparticle by using the curcumin as the reducing agent, and we will do the I will also show the molecular interaction of curcumin with this silver nanocluster using this DFT calculation. We have performed the geometry optimization, UVB TD-DFT calculation, and IR frequency calculation, and we have compared these results with the experimental one. So this is the synthetic procedure. Here we see that this silver nanoparticles has been synthesized in alkaline solution using this curcumin. We have synthesized two types of nanoparticles. One is having 1:1, means we have used curcumin and silver nitrate as 1:1 ratio, and another A1. This is A1, and A2 is for 1:0.1. And this is the XRD graph of this.
Your slide is not moving. Just move the slide also. Slide only the title slide is there.
Okay, just a minute, sir.
Yes. Now it is moving.
Now it's moving, no, sir?
Yeah, it is moving now.
Okay, so this is the synthetic procedure, and here A1, this A1 peak belongs to the synthesis of silver nanoparticle as 1:1 ratio. One is AgNO3 and one proportional for the AgNO3 and curcumin, and this A2 is for 1:0.1 ratio. Next, we have done. This is the IR spectra of those both the complexes A1 and A2, and these are the IR frequency calculated from the DFT calculation, and all these peaks has been assigned using this DFT calculation, IR frequency calculation. This is for, we have correlated this experimental and DFT data for the IR frequency, and we found here that a very good correlation is being seen in the experimental and theoretical cases. This is the UV visible spectra of A1 and A2 samples, and these vertical lines correspond to the TD-DFT calculation, which is for the different transitions occurring in the compounds, silver cluster to the Ag curcumin, like that. These are the TD-DFT result, various transitions occurring at different wavelength. And these are the oscillator strength and the transitions and the band assignment. That is from the which molecular orbital to which, different molecular orbitals. This is the frontier molecular orbital picture. Here we see that the HOMO is present on the silver nanoparticle, whereas the LUMO is present on the curcumin in the ground state. And in this belongs to the molecular interaction. We actually, what happens, curcumin exists in two parts. One is in cis part and another is trans. So cis curcumin, here in cis curcumin, we see that the CO bond, both the CO bonds belongs to the same side. Whereas in trans, this CO bond belongs, one is up and the just other is down. But when we do the geometry optimization, we found that Ag13 trans curcumin is very much stable as compared to the cis curcumin. So we conclude that this nanoparticle being formed is quite stable as compared to the cis one. And for this reason, we have carried out all the calculation, DFT calculation for the trans curcumin only. Here also we see that only a single interaction is being seen for the cis one, whereas for the trans one we are seeing with the same oxygen, two interactions are being seen with the silver clusters. Next, we have carried out the electrostatic potential charges, and we see that in the ground state, this orange color represents the negative charges, whereas this yellowish green color represents the positive charges. In the ground state calculation, we see that the negative charges are present on the silver cluster, outside of the silver cluster also. Whereas in excited state, when we do the calculation, transition state calculation, we see that the silver cluster, all the yellowish part is only there here, but negative charges are present on the curcumin side only. So this is for the high, here we have seen that the HOMO in the ground state for the silver cluster is present on the curcumin silver cluster, whereas LUMO is on curcumin. Whereas in the excited state, we see that the pi star of the curcumin is behaving as the HOMO, whereas the AG silver cluster acts as the LUMO here. Means electron charges are present mainly here only. Another thing is that here we see the density of a state plot. This is for the curcumin, and we can clearly see here that for the curcumin, the band gap is quite higher. Green corresponds to the HOMO and red for the LUMO. The band gap for the curcumin is quite higher. This is for the silver cluster. And here also we see that there is a difference between this HOMO and LUMO. But in case of when we combine Ag13 with the curcumin, we see that there overlapping is occurring. Means electronic transition are becoming very easier when we are combining the silver with the curcumin. Next, we see that the curcumin not only act as the capping agent or the reducing agent, but it also catalyzes the reaction by decreasing the band gap, as we are seeing here only. Means silver, with the addition of silver and curcumin, the band gap decreases. So curcumin not only acting as the reducing agent, but it also decreasing the band gap, and it catalyzes the reactions also. Next, here we see the Mulliken charge distribution of curcumin. Here we see that the negative charge, as red color represents the negative charge, and the green color represents the positive charge on the atom. So the negative part of the silver are negative here, and on the curcumin, both the negative and positive charges are present. Further, we have when we have synthesized the silver cluster using the curcumin, we carried out the photocatalytic degradation of organic pollutants such as the paranitrophenol or nitrobenzene also we have carried out, and the methylene orange also. Here I am showing this PNP only, and we see here that there is a huge decrease, means degradation of this PNP, and it occurs at the 406 nanometer. And after that, we have carried out the photo degradation using this glycerol as the reducing agent of PNP. It follows the second order, whereas in case of when we use the NaBH4 as a reducing agent, we see that the reaction order is generally came to be zero order or the pseudo first order reaction. But when we are using the glycerol and PNP, in this for this catalyst, we are obtaining the second order reaction for the thermal degradation. But when we are doing the same reaction in photocatalytic, when we are doing the photocatalytic studies, it follows the zero order kinetics here. So it is of great importance that the photocatalytic, there is a huge difference when we are trying to do the different reactions using the thermal or the photocatalytic. Their behavior are very different. And finally, I would like to conclude that the DFT calculation here proves to be very useful tool in finding the molecular interaction between the curcumin and the silver cluster. We have carried out many of the DFT calculation for the cuprous oxide and silver and curcumin, and then PVP like that. And we also carried out the photocatalytic degradation type. Means we have find the mechanism how these transitions are occurring. So DFT calculation proves to be a very good tool for this cluster system also. And the experimental results such as the IR or UV has been analyzed well with the help of TDDFT calculation or frequency calculation using this DFT. And the strong binding interaction of the electronic structure changes observed suggest that the potential of curcumin serves as the stabilizing agent for the silver cluster. We have also seen by doing the molecular geometry optimization. And also we have seen that this DOS calculation shows that the curcumin is decreasing the band gap between the silver and the curcumin, and it catalyzes the reaction further. Finally, I would like to acknowledge this UGC for the startup grant project and the computer unit IIT BHU for providing the computational facilities. And thank you. And I think I am within the time. So thank you. Any questions? You are welcome.